You may think this is mathematics, or this, or this. Well, actually, this is how mathematics looks like. In this video, let's dive deeper into the rabbit hole of algebra to see how complicated that is to show something that is seemingly obvious in mathematics. Side note, this is the first video of me teaching myself graduate level mathematics to understand the inner workings of cryptography, which is related to my other two projects of a secure telemetry system for a model UAV and a CLI tool for PC-to-PC messaging. Do I need to understand the underlying mathematics to build them? I don't think so. But do I want to show off publicly that I'm not just an engineer who builds stuff that works, but also internally a purist about learning rigorous mathematics for its own sake? Definitely. So without further ado, let me torture you with my delusional sense of superiority. By the time we're in high school, hopefully multiplying monomials becomes our second nature. We rarely doubt about whether the ways how we manipulate symbols are legal, yet I believe there are always a few students in the class that are so confused about it. Ironically, in some sense they think more like a mathematician than those students who just apply the rules. One of the quote-unquote dumb questions that students might ask is, why can we add brackets wherever we want in the product? Before answering this question, let's frame this question in a more rigorous way. Problem: let G be a monoid and x1 to xn are elements of G, where n is an integer larger than 1. Define the product of these elements inductively in the following way. Some symbols equals to some other symbols equals to yet another bunch of symbols. Show that the following equation is true. Now you might have a problem with me saying these symbols, those symbols, and other bunch of symbols. You might think, I already took a calculus course, I know what that means. I don't doubt that you know what that means for application purposes, but since what I'm doing here is giving a mathematical proof, let's pretend we don't know yet. Otherwise, we might get into a flawed argument that assumes the target statement as true in the first place. So let's start with some clear definitions. When I look at this problem, the first thing I need to ask is, what is monoid? So let me make a map to keep track of all the definitions. Definition of monoid. A monoid is a set G with a law of composition which is associative and have a unit element. I don't know about you, but I do get more confused with more terminologies, so I need to tackle them one by one. The first one is law of composition. Definition of law of composition. Let S be a set. A mapping from S Cartesian product S to S is sometimes called a law of composition of S into itself. Hopefully this definition is clear to you. It's definitely clear to me. If you need more explanations for this or any other following steps, feel free to leave a comment below. I'll make a video answering your questions. Now let's get back to the definition of monoid. The next term that needs to be defined is associative. Definition of associativity. Let S be a set with a law of composition, which means there exists a map that takes two elements from S and maps them to S itself, according to the previous definition. If X, Y, Z are elements of S, then two products can be formed. X product Y bracket, product Z, and X product Y product Z bracket. If these two products equal to each other for all X, Y, Z in S, then the law of composition is called associative. You might think this definition of associativity is clear enough, but just in case I bring some extra unnecessary assumptions about the term product into this whole argument, I would like to go one layer down to also clearly define what is a product. Definition of product. If X and Y are elements of S, the image of the pair XY under the mapping S Cartesian product S to S itself is called their product under the law of composition and will be denoted by XY. So this means that this is not the type of product in the normal multiplication sense. We haven't defined anything as multiplication yet. So this product can be an addition, a subtraction, or some other type of mappings, as long as this map takes two elements of S and maps it back to S itself. Thus, I said let's pretend that we don't know anything about the symbols, because those are entirely different beasts from what we think we know. Now going back to the definition of associativity, everything is clear without additional unnecessary assumptions. Then let's go back to the definition of monoid. The last term that needs to be defined is unit element. definition of unit element. An element E of S such that Ex equals to X equals to Xe for all X in S is called a unit element. Here I omit the one-line proof of the uniqueness of E. I believe you can figure it out by yourself. Now that I have covered all of the terminologies in the definition of monoid, I can go back to the problem itself. Let's rewrite the problem to a more fundamental language. Problem: let G be a set with mapping from G Cartesian product G to G itself, such that for all xyz in G, x product y bracket product z equals to x product y product z bracket. This is the first condition. The second one is there exists exactly one E in G, such that for all x in G, Ex equals to x equals to Xe. And the third condition, x1 to xn are elements of G where n is an integer larger than 1. Then define the following product inductively and show that the following equation is true. After all of these preparation, then we can try to understand the key part of the problem. This highlighted part is not the normal equation that tells you the symbol on the left hand side means multiplying all the elements from x1 to xn. Instead, it means this symbol is defined as the product of two elements. One is reducing the maximum count of the symbol by 1, the other one is the element with the previous maximum count. Continuously doing this recursively, then we reach to a product of x1 and x2. Since the problem defined that n is larger than 1, this is the base case of the recursion. This particular clarity is all we need to solve the problem. No other intuitive understanding is needed, neither what the symbols means, nor any higher level explanations. So let's move on to the actual solution. Consider this particular symbol, which is the second part of the left hand side of the equation that we need to show is true. First, let's write down the expanded version of this symbol, then apply the associative property. We can get the following expression. Then do it again. Continuously doing it, we'll get this final expression. Then substitute the result to the product of these two symbols, and apply the associative property again until this line, which matches the definition of the symbol. Thus, we show that this equation is true, which essentially asserts that parentheses can be inserted in any manner in the product without changing its value. In other words, we answered the question, why can we add brackets wherever we want in a product without requiring us knowing what is multiplication? This is the key of mathematics. To quote from Wittgenstein, mathematics is a logical method. Mathematical propositions express no thoughts. In life, it is never a mathematical proposition which we need, but we use mathematical propositions only in order to infer from propositions which do not belong to mathematics to other which equally do not belong to mathematics. All of the mathematical theorems are the same, namely tautology. It's not the understanding of mathematics itself that's important, but its formal logical system. Mathematics doesn't carry any meaning at all, but its implications do. I hope you learned something from this video. If not, at least remember, mathematics is not what you think. That's it for now. See you in the next one.